There we go. Okay, so today we're going to be discussing here in-core printed circuit heat exchange in molten salt reactors. And the reason that we're interested in this is for the purpose of increased power density while maintaining kind of more of a small modular scale, or at least similar. So in generation 4 reactors, there's a number of different types. We have sodium fast reactors, gas-cooled reactors. Molten salt reactors are among those that are proposed for generation 4. And one of the unique things about molten salt reactors is that it uses a liquid fuel, and that fuel can has some the ability to transfer heat in unique methods that are different than using solid fuel, because we're able to flow the fuel outside the core. And so generally speaking, what happens in a molten salt reactor is we'll see a loop something like what's right here on the right. We'll see an active core region, usually with a moderator, not always. And then that will transfer outside of the core to a heat exchanger where the primary heat exchange takes place. Whereas in a PWR, for example, you'd have the primary heat exchange taking place in the core with heat being transferred from the fuel rods directly to water, which is the primary coolant. So in this case, you'd be transferring from a primary fuel fluid to a secondary fuel coolant. But what I'm proposing here is a concept where we will, rather than have heat exchange take place outside of the core, we'll have that heat exchange done inside of the core. So this could be in addition to heat exchange outside the core if your entire goal was for increased power density. But what I'm going to examine here is this setup here on the right that is going to offer us a few qualitative benefits in addition to increased power density. So we're going to have no heat exchange occurring outside of the core. And it will, so one side of the core will also be the primary heat exchanger. It'll be in a kind of a printed circuit heat exchange configuration. And we'll have a coolant running on one side and the fuel running on the other side in kind of interlaced layers. And so, so just so we kind of understand what that means in terms of reactor behavior and performance, at steady state, we're going to see average core temperatures that are determined primarily by the neutronics of the core. And so temperature is not going to change with heat transfer at steady state. Of course, it will in the transient case, but it should be determined by neutronics. And then we can think of the rate of heat exchange and the power produced as being primarily determined by the thermal hydraulic system. So the rate of fuel flow and coolant flow and all of those things will be what really determines how much heat we're producing. So just so we have kind of some visual examples of what we're going to be thinking about and what the calculations are going to represent. The figure on the right is what you would expect to see in stacked, kind of this stacked interlaced printed circuit heat exchange setup. So you have channels going through on the right side of that heat exchanger, and those would be from one fluid, say the coolant fluid, and then you might have the fuel fluid on the left side there going in at a different angle. And so those would be in layers. And one of the calculations, just so we have a good idea, is going to be done through this, there's kind of this S-curve fin pattern. Rather than channels, some of the calculations are done using Nusselt number correlations for these fins here. Whereas relap calculations, which will be shown later, are going to be performed using channels. It's using the Nilinsky correlation for channeled flow. So why do we find this important? Why would we want to do this? So obviously we can have increased power density regardless. That can be, not everybody designs a molten salt reactor for the highest power density, particularly when graphite is involved. We're going to ignore that for the purposes of these calculations. We're kind of looking to maximize power density. It's because it's one of the benefits that I see from this technique. And so we're getting significantly higher power density regardless, but definitely if you're using external heat exchange as well, you can get really high levels of power density, as much as 1 gigawatt thermal per meter cubed. Now, when we look at no external heat exchange, we can get a nearly flat axial temperature profile. So we'll see some specific numbers later, but what we're seeing is that a maximum of 7 degrees C is our axial temperature profile. And this is because essentially you are cooling with the coldest, coolant at what would be the highest temperature in a normal reactor, where you have the fuel coming out at the top axially. That would be where you would normally experience your highest temperature. In this case, that temperature is going to be the same as the inlet temperature, and there'll be a small peak towards the middle. We're going to eliminate the hot leg, cold leg corrosion that can be sometimes a challenge in molten salt reactors, because the fuel is not exchanging heat outside the core. It's actually coming out at the same temperature that it's going in. And so we don't have that cold leg deposition and hot leg corrosion in the core loop. And then we're also going to be able to minimize the amount of salt volume outside of the core, which means that we can flow that salt more quickly back into the core and have our delayed neutron precursors, then more of them are going to be decaying in the core. And that helps us in terms of control. So molten salt fuel has a few properties that are going to allow us to increase the power density inherently, but we haven't seen those utilized to the greatest extent. And again, there are many reasons for that. Sometimes reactor designers are actively trying to lower power density, but what you can see here is that sodium fast reactors tend to have the highest power density, sometimes as much as sometimes over 400 megawatts per meter cubed, whereas molten salt reactor designs up until now have been in the range of maybe 30 to 60 megawatts per meter cubed of core volume. So why do we care about maximizing power density? Obviously, economics are better if you can have more power rather than less, assuming all else is equal. We'd always like to be producing more power because that's kind of the goal of the power plant. It makes the cost of it come down as the economy of scales increases. And it also means that we're going to have lower materials cost for building it on a per megawatt basis. And then being able to do that with a relatively small reactor size allows us to gain economies of repetition. And that can be of benefit both in terms of constructing reactors and in terms of maintenance. If you have many smaller cores on a single site, you can have higher capacity utilization of specialized labor and equipment that you're using to maintain those reactors. So, oh, looks like we have a repeated slide here. Okay. So our estimated theoretical power density, just so that we have a good basis of comparison, this is what we would be looking at if we were trying to compare to kind of a standard molten salt reactor design. So 70, looks like 70 to 170 is about the range that we're looking at, megawatts per meter cubed. And when we compare that to what we get in our printed circuit heat exchange core, we are looking at about double on average the amount of power produced. So on the low end, we're starting here at about 140 or 160 megawatts per meter cubed, and we go as high as 422 megawatts for that 1 meter cubed volume. So that gives us twice as much power on a per volume basis compared to a conventional core, and it reduces volume of the heat exchanger. Well, really you have no heat exchanger outside the core now, but compared to a standard shell and tube, you're reducing that by 5 to 6 times. And these are all for fairly reasonable pressure drops. So we're only getting maybe 1 to as much as, actually on the higher end, some of these are, this one's 9.5 bars. So that's the highest pressure drop that you're seeing here. And then, and we find that these results are matching fairly closely, both for the hand calculations done using NTU method, as well as the simulations done in Relap 5 3D. So this is the temperature distribution that we were discussing earlier. We'll see that our axial distribution for a counterflow setup is going to be, so our maximum delta T on the lower end is 4.6 degrees C. That's for a slower flow rate and lower thermal power. And then on the higher end, we're seeing as much as 6.5 degrees C. So that's a very low temperature distribution. And then, so we've discussed results and benefits. There's a few pretty serious limitations. Obviously, this is a somewhat academic and theoretical exercise at this point. So there's a serious issue with graphite lifespan. And so these current calculations envision using graphite. There are obviously other potential options. Silicon carbide works neutronically. According to the estimates I made, you could also look at things that are more exotic, like industrial diamond, which seems to be coming down in price, but is probably not economical right now. And then metals are also potentially usable, but you would be in a fast spectrum at that point. And it may require higher fuel concentrations than may be allowable under a lot of licensing regimes. So there's also a question of, depending on the material, if we're using these ceramic materials, how are we going to manufacture that core? How are we welding layers together? And then if we're using a ceramic material, what is the metal piping interface going to look like if we're trying to interface metal piping with a ceramic core? So those are all topics for future work outside of the scope here, but things that could be interesting to explore. Any questions?
Thank you, Craig. Any questions?
Hold on, let me stop sharing.